Hello, so in this video we're going to carry on talking about separable equations, and I'm actually going to kick this video off with an example, and the example is 3xy plus y squared plus x squared plus xy lots of dy by dx equals 0. Okay, now remember what we want to do is we want to get it in the form of, in order to do the separable equation, the form of a function m, which can be of x and y. I'm just going to drop the dependency on x and y because I think you're kind of familiar with that now. It just kind of gets in the way to see what's going on. Times some other function which is multiplied by dy by dx, okay, equals 0. And we can also get it into differential form just by multiplying through by dx. Okay, so it looks like this. Right. So basically that's the idea. Well, I'm just going to leave it as dy by dx for the moment. Okay, so leave it like that for the moment. So when we look at this equation up here, can we get this in separable form? Well, yes, we can. The kind of difficulty thing with, the most difficult thing with these kind of questions is really working out what m and n are. And actually, that's not really that difficult at all. So actually, these questions are relatively straightforward. Okay, well, hopefully you can see the function being multiplied by dy by dx is this one here, the x squared plus xy. So that means that that must be n. Okay, so in other words, I know that n is equal to x squared plus xy. Then the other function is this one here. Okay, so therefore that must be m. That must be m. Okay, so m equals 3xy plus y squared. Okay, now in order for these, we need to check the exactness of these equations, and in order for them to be exact, we basically need that the derivative of m with respect to y has got to be equal to the derivative of n with respect to x. I always think that when you're checking the exactness, it's kind of the opposite of what's associated with. So if I just multiply through by dx now, okay, the m here is associated with a dx, okay. Well, when I'm checking the exactness, it's the opposite, okay. So it's m differentiated with respect to not x, but y, okay. And likewise for n, it's n differentiated with not y, but x. Okay, so basically this is to check the exactness. So let's check the exactness of this equation. So m with respect to x, so in order for them to be exact, we need these two things to be equal to each other. So m with respect to y, so it's this equation, differentiate with respect to y. Well, we differentiate with respect to y, which means that everything that's not y, including x, is a constant. Okay, so x is a constant, effectively. So let's differentiate this with respect to y. Well, 3x is a constant. Then the derivative of y with respect to y is just 1, so it's just going to be 3x, okay? Then let's differentiate the y squared with respect to y, so therefore that's going to become 2y, okay? Now let's check the derivative of n with respect to x, so let's look at this one. Well, we're differentiating with respect to x now, so therefore anything which isn't x is a constant, okay? And that includes y. So x squared differentiated with respect to x is going to be 2x, okay? And then xy differentiated with respect to x, well, y is just a constant, okay? Y is just a constant, and x differentiated is just going to be 1, so it's going to be y here. Okay, well, you can see that clearly those two things are not the same. Those two things are not the same. So therefore, because they're not the same, they are this equation is non-exact. Right, okay, so it's non-exact. So therefore, we can't just do what we were doing in the last video when it was exact, because if we show it's exact, then basically we say, right, okay, suppose that some function exists such that it's equal to the integral of, or the derivative of that is equal to m, and the derivative of that function with respect to y is equal to n, okay? We can't do that because they're non-exact. We can't do that, so they're non-exact. So what we're going to have to do is we're going to have to use something called, what I like to call a fudge factor. Basically, it's a function that makes these equations exact, okay? It's a bit like when we're doing with the integral example, the integration factor example. We had to multiply through by a constant or some function to basically get rid of one of the terms to make it easier to deal with, okay, with a variable coefficient case. Well, now what we've got to do is multiply through by some function that makes it exact, and this function makes it exact. So what is that function? Well, let's call that function mu, okay? And basically the idea is that when we multiply through by mu, we get we make it exact. So what have we got? Let's just write down what we've got. We've got m, okay, and m is a function of x and y, plus n times dy by dx has got to be equal to 0, okay? And basically the idea is that if we want it exact, then basically the derivative of m with respect to y has got to be equal to the derivative of n with respect to x. So that's kind of what we're after. We want to make this thing exact just by multiplying through by a suitable function, and that function we're going to call mu. So in other words, when we multiply through by mu, so we multiply this by mu and we multiply this by mu, then basically, when we now take the derivative of this thing with respect to y, so we take the derivative of this thing with respect to y, and the derivative of this thing with respect to x now, so this is basically our new, this is like our new functions, okay? Then basically, this then becomes exact. Oops, it should be that thing with respect to x. Then basically, this makes it exact. Right. So what is that mu? Well, let's find out an expression for this mu. Let's expand this thing out. So let's expand this thing out. Well, this is just going to be the product rule, okay? Because if we assume that mu is a function of x and y, then therefore this is going to be a product rule, because when we differentiate mu, which is a function of x and y, and m, which is a function of x and y, with respect to y, so we can differentiate both mu and m with respect to y, then therefore this is just going to be the product rule. So it's just going to be the derivative of mu with respect to y multiplied by the m left alone. Okay, so we've multiplied that differentiated that with respect to y, left that one alone. Okay, plus the other way round. So that thing left alone, the mu, multiplied by the m differentiated with respect to y. Okay, so that's that thing. And we basically want that equal to the same thing, but this time with mu n differentiated with respect to x. So it's product rule again. So it's mu with respect to x multiplied by n left alone, plus the other way round, plus mu left alone multiplied by n with respect to x. Okay, so this is what we've basically got. This is what we've got. Okay, now what I'm going to do is I'm going to get all the terms on one side. Okay, because what I want to basically do is try and come up with an equation for mu which I can solve. So I've got mu y times m plus mu times my, and then I'll take these two terms on the other side, so I end up with minus mu x times n minus mu times nx, and that's all going to be equal to 0. Okay, so this is what I end up with now. Okay, now I've got a mu here and I've got a mu here. So what I'm going to do is I'm going to factor out a mu. So I've got mu y times m, can't really do much with that, and a mu x minus mu x times n. So I've got these two terms, but I'm going to factor out a mu now. So plus mu, lots of, what have I got? My minus nx. Okay, and that's equal to 0. And now basically I want to try and rearrange to find mu. Well, the thing is, I can't as such, because look, I've got mu differentiated with respect to y, mu differentiated with respect to x, and just an ordinary mu function. So this is a differential equation. It's a differential equation, so I know that I'm going to have to be solving a differential equation. But look what happens. Look what happens. At the moment, this is what's known as a partial differential equation. This is a partial differential equation. Actually, I'm going to put the mu at the end there. Equals 0. I'm just multiplying by mu still. I've just written it in a different place. This is a partial differential equation. The reason why is because not only have I got the derivative of mu with respect to y, but I've also got the derivative of mu with respect to x. Okay, so this is now a partial derivative. This is, if you like, the partial derivative of mu with respect to y. And this is, if you like, the partial derivative of mu with respect to x. So, in other words, I've got the partial derivative of mu with respect to not just x, but also the partial derivative of mu with respect to y. So I've got two derivatives for mu. Well, that makes it a partial differential equation. We don't solve partial differential equations in this course. Okay, so as it stands, we can't solve mu. But let's suppose that mu is just a function of one variable. So let's suppose mu is just a function of x. Or, let's consider the other case as well, that mu is just a function of y. Well, if mu is just a function of one variable, okay, then therefore one of the derivatives must disappear, because, if mu is just a derivative of, let's take the case when mu is just a function of x. By the way, we can do that because we're completely in control of what mu is doing, okay? And, in actual fact, this is how we kind of solve it in this course. It's the reason why it's in this course. It's an ordinary derivative. So we just assume that mu is a function of one variable and one variable alone, okay? So we don't have to solve a PDE. So let's suppose that mu is just a function of x. So if mu is just a function of x, okay, then basically we can't differentiate mu with respect to y because there's no x involved in the function. There's no x involved in the function, right? So we can't differentiate it with respect to y. So therefore this term just goes to 0. Okay, so what we're left with is we're left with minus mu x times n, okay, plus my minus nx times mu. Well, this is still an ordinary differential equation. It's still a differential equation because we've still got mu with respect to x and we've still got a mu involved. Okay, but it's no longer a partial differential equation. It's an ordinary differential equation because we've only got the derivative with respect to one variable. Okay, so let's just rearrange to try and solve this. This is equal to 0. Let's just rearrange and try and solve this. So, in other words, I'm just going to take this mu x over the other side, or sorry, mu x times n over the other side. So I'm left with mu x times n. So I'll take it over to the other side, and I'll just write it around the other way. So mu x times n, okay, has got to be equal to my minus nx times mu. Okay, and let's just divide through by n. Divide through by n. I'm actually just going to rewrite this mu with respect to x like this. So d mu by dx. So in other words, when mu is just a function of x alone, we have to solve this partial differential equation. Sorry, not partial differential, ordinary differential equation. Okay. Now let's consider the other case when mu is just a function. When mu is just a function of y alone. So let's just consider the other case when mu is a function of y alone. Well, when mu is a function of just y, then therefore we can't take the derivative with respect to x because it's only a function of y. So we can't take the derivative of x. So in other words, this is just going to go to 0. So what we're left with is mu y times m, okay, plus my minus nx lots of mu. So what are we left with? We're left with m lots of, so mu y lots of m, my lots of m, mu y lots of m, okay, plus my minus nx, lots of mu, and that's all equal to 0. So that's just when it's a function of y alone. Okay, let's rearrange this to get mu y on its own. So mu y times m is equal to, it's going to be negative my minus nx lots of mu. Okay, let's just multiply through by this negative, so we end up with negative my plus nx. Okay, just rewrite it around the other way so it looks a little bit neater. So it's nx minus my. Okay, let's just divide through by m. Let's change this mu by mu y just to change it to d mu by dy, the more familiar form of writing it. And this is now an ordinary differential equation that we have to solve when mu is a function of y alone. So now what we've got is we've got two ODEs that we can solve for mu. Okay, and in actual fact, either one will work. And actually, you know, I really encourage you that if you're kind of trying to solve one ODE with, you know, when you're trying to work out what mu is and you're trying to solve one of these ODEs, say if you're trying to solve this, you know, trying to work with this to find out what mu is, this mu d mu by dx, and it's not quite working or it's coming out quite nasty, then a good tip is try and solve the other one. Try and solve with d mu by dy, because one of them will always be relatively easy to solve. Also, another trick is that most often mu will come out as something like mu equals x or mu equals 1 over x or something like that. Okay, so I'll just write down what the equations are again. Well, actually, what I'm going to do is I'm going to do it with you. So basically, I'm going to show you a quick way of kind of remembering which one's which. So basically, say if I wanted to remember what d mu by dx is, okay? Okay, so basically what I do is I look here, and it's always the second term that I look at. I'll try and show you what I mean by that. So I look here, so I know that I'm differentiating with respect to x, which means that I know that the second term in my denominator, so this one, will be the derivative of, you know, whatever the derivative of x is. So I know that it's n differentiated with respect to x, and m is differentiated with respect to y. Okay, so in other words, I know that my second term in my denominator will be nx. I know that my second term in my denominator, which means nx. There's always a minus in the middle, which means that I know my first one must be the other one. So it's my. Okay, then again, I look at this second term, I see it's an n, so therefore there must be an n on the denominator. Okay, then I just multiply that by mu. Likewise, for d mu by dy, look at this y, okay? Therefore, I know that my second term in my numerator must be the derivative with respect to y. Well, what's the derivative with respect to y? It's the m one. So it's m differentiated with respect to y, which means that my first one must be nx. And there's always a minus in the middle. Then again, I look at this second term. I see it's an m with respect to y, which tells me there must be an m on the bottom, okay, times mu. So that's kind of how to work out which one's which. And you just solve either one of those to find out what mu is. Okay, so let's go back to our example again. Okay, so this is all the information that we've got with our example. Okay, so this is the original one. This is our original equation that we had before, and we worked out what m and n was, and we worked out what the derivatives were as well. Well, now what I want to basically do is I've shown that these two things are not equal to each other. These two things are not equal to each other, so therefore this equation is not exact. So basically, I want to multiply through by some integrating, or some fudge factor, effectively, mu, such that, you know, when I multiply mu m times, so mu m, the derivative of mu m with respect to y, is equal to the derivative of mu n with respect to x. Okay, so let's just multiply through by mu m. Okay, so basically the idea is that I want to solve this OD to find out what mu is. So I want to find out what mu is. Okay, so it's just using this same either one of these as before. Okay, so I'm just going to use this one actually. I'm just going to use d mu by dx. Doesn't matter, but I'm going to use d mu by dx. D mu by dx. So what's the formula? Well, I look at what I'm differentiating with respect to, and that tells me what the second term on the numerator is going to be. So I'm differentiating with respect to x. So therefore, my second term must be n with respect to x. Okay, my first term then must be n with respect to y. Again, look at my second term. What's going to be on the denominator? It must be n. Okay, and then I'm just multiplying that with respect to mu. Okay, so basically I'm trying to solve this. So what is n with respect to y? Well, n with respect to y is 3x plus 2y. Then nx, so it's minus nx, which is 2x plus y. Okay, on the denominator it must be n, which is this one, so x squared plus xy. Okay, that's all multiplied by mu, and I'm trying to solve d mu by dx. Okay, so let's just simplify this numerator. So multiply 3 by minus, so I end up with that. Okay, then what's 3x minus 2x? So this is 3x minus 2x, which of course is 1x. Okay, then 2y minus y, so that must be plus y. Okay, and on the denominator I'm going to factor out an x. I'm going to factor out x of this thing. So I'm left with x times x plus y times by mu. Okay, so I'm left with d mu by dx is equal to that. Well, look, I've got an x plus y on the numerator and x plus y on the denominator, which is left. Okay, so that basically means that d mu by dx is equal to, what am I left with? 1 over x times mu. 1 over x times mu. Okay, so this is a nice simple ODE that I can solve just by separation of variables, right? Just to everything involving x on one side and everything involving mu on the other side. So this then becomes, if I just divide through by mu, I'll end up with d mu times d mu by dx equals 1 over x, and then get everything involving x on the other side by multiplying through by dx. And then just take the integral of both sides. So that means that basically this thing differentiated with respect to mu is natural logarithm of mu. This thing differentiated with respect to x is, or integrated with respect to x, is going to be natural logarithm of x. Okay, so I've got the natural logarithm of two things. So I've got the natural logarithm of mu is equal to the natural logarithm of, of x. Are you happy then that the thing inside the argument, the thing inside the brackets, is just going to be the same? So therefore I can say that mu is just going to be equal to x. And like I say, you know, normally this comes out as something relatively straightforward. It either comes out as x, or it comes out as mu. It comes out as x, or 1 over x, or something like that. Equally, just in case you don't believe me, you can equally go and sort of try and with this, see if it works. So try it with this equation and see if it works. But for the moment, you know, I've found out what mu is. I'm happy. So now the idea is that I want to make it exact. So therefore, I want to show that mu with respect to m differentiated with respect to y has got to be equal to mu times n differentiated with respect to x. Okay, well, what is mu times m? Well, let me just write out what everything was again. Okay, and we had as well that mu was equal to x, so this is what we're working with now. So basically mu times m, so in other words what I'm trying to do is x times 3x y plus y squared. Okay, I want to now show that it does actually work. And that's all differentiated with respect to y. Should be equal to mu times n. So mu times n is x times n, which is x squared plus xy. Okay, and that's all differentiated with respect to x. So I want to basically show that those two things are equal to each other. Well, what's this? This is going to become 3x squared plus xy squared. So xy squared differentiated with respect to y. Okay, differentiated with respect to y. And this is then going to become x cubed plus x squared y. Okay, differentiated with respect to x, differentiated with respect to x. So therefore, what's this differentiated with respect to y? Well, it's going to be 3x squared, right, plus 2xy. Okay, so this is what the left-hand side. And then the right-hand side is differentiated with respect to x. It's going to become 3x squared, looking good already, plus 2xy. They're equal, so therefore they're exact. So basically, we found an integrating factor, a fudge factor, if you like. Sorry, not an integrating factor, a fudge factor, mu, that basically makes these two equations, basically makes this equation exact. So we have to multiply through by mu to make it exact. Okay, then we can just go forward and try and solve it. So therefore, what we basically do now is we're looking for some function. Which, when differentiated with respect to x, is equal to not just m, but now mu times m, because we now need to use our fudge factor. Because remember, we need to use our fudge factor to make it exact. So therefore, we can't just ignore the fudge factor in later examples, okay? We basically need that fudge factor in order for this method to work. So we have to now consider mu times m, okay? And likewise, we know that our function differentiated with respect to y must be equal to not just n, but mu times n, okay? So in other words, we know that differentiate, so the phi with respect to x is going to be equal to mu times x. Well, what was mu times x? It was this thing here. Yeah, it was equal to 3x squared times y plus xy squared, okay, and we know that phi differentiated with respect to y is equal to mu times n, so it's this thing here. So x cubed plus x squared y, okay. So now what we basically do is we just choose one, either that one or we choose that one, okay. So I'm going to choose this one here, I'm going to choose this left one here. So basically I know that the derivative of phi with respect to x, so it's a partial derivative, should be equal to 3x squared times y plus xy squared, okay, which basically means that phi must be the integral of that with respect to x. So if you like, the derivative of that with respect to x must be equal to that. So therefore, the phi must be equal to the derivative, must be equal to the integral of that. Okay, that's fairly obviously integral and derivatives, two opposite things. So let's work this out. So we end up with, well, integrating this with respect to x, raise the power by 1 and divide by the new power. So we end up with 3 over 3 x cubed, that's just 1 times y. So we just consider again y as a constant, that's fine. Okay, then again we just consider y as a constant in the second thing. So y is a constant, so therefore we've got half x squared y squared. Okay, plus some constant of integration. That constant of integration will be dependent on y. Okay, the reason why it's dependent on y, I'll just go through it again. The reason why we know it's dependent on y, because remember the derivative of phi with respect to x must be equal to that. So therefore, well, it must be equal to that, sorry. So when we differentiate that, we need to get that back, essentially. So we differentiate this x cubed y plus half x squared y squared plus cy. We need to differentiate that with respect to x, and we should get that thing inside the, the integrand inside the integral. Okay? Well, if this is a function of y alone, then when we differentiate with respect to x, then that's just going to be treated as a constant, so it's just going to disappear. Okay, so that's why we know it must be a function of, the constant must be a function of y. Okay, well, what also do we know? Well, we know that phi with respect to y is equal to x cubed plus x squared y. So phi with respect to y, so maybe if I write it out, derivative of phi with respect to y must be equal to, what was it? X cubed plus x squared y. X cubed plus x squared y. Okay, just from that thing up there. So basically, if we now know that phi is equal to that thing, phi is equal to this. So basically, the idea is that we want to try and work out what this constant is. Okay, and the way that we can work it out is by knowing that derivative of phi must be equal to that with respect to y must be equal to that. So if we now differentiate this thing with respect to y, okay, then we should be able to work out what the constant is. Okay, so let's work out what the derivative of phi is. So let's work out the derivative of phi with respect to y. Let's work out the derivative of this thing with respect to y. Again, just treat x squared, anything involving x as a constant. Okay, so x cubed is just a constant. Y differentiated just goes to 1. Okay, plus, well, this is going to become 2y. Okay, and then just multiply by half x squared. So it's going to become 2 times a half. That's going to be 1. Okay, times x squared, lots of y. Okay, plus, and then the derivative of this constant with respect to y. So it's just going to be c dash of y. Okay, and we know that those two things must be equal to each other. So therefore, we know that x cubed plus x squared plus x squared y plus the derivative of c with respect to y must be equal to x cubed plus x squared lots of y. Okay, so therefore, in order to work out what c is, let's get that on its own. So let's take everything not involving the constant on the other side. So that's equal to x cubed minus plus x squared y minus x cubed minus x squared y. So I've just taken those two things on the other side. Okay, so now that implies that the c, the constant with respect to y, must be, well, actually, first of all, let's get rid of those, that's x cubed, because they just cancel off. Okay, and actually those two things cancel off. So that thing must be a 0. So therefore the, c must be equal to 0 as well. Because if the derivative is equal to 0, then c itself must be equal to 0 as well. Okay, the reason why it's not some constant as well, because remember when we said, if we say the derivative of something is 0, then when we integrate it, it should be a constant. Because when we have a constant and we differentiate it, So when we have a constant, and if we differentiate it, then we should just get 0. Well, the reason why we know it's not 0 is because we know it must be a function of y alone. From up here, we know that this must be a function of y alone. Well, therefore, because we get that the function differentiated with respect to y is just going to be the thing itself, then it must be 0. Because look as well here. If you don't quite follow that logic, or you can't quite see that, perhaps that's not explained the best way, I appreciate. But if you can't quite see that, let's just look up here. We basically need that these two sides are going to be equal to each other. Well, look, if we don't have that function, if we don't have that there, then they already are equal to each other. Yeah? So we don't actually need any kind of extra constant. So therefore we do know that it's just going to be 0. That's just kind of a quick justification of why it's 0. I've just kind of gone through the general method down here. But that's how we know it should just be 0. So in other words, we now know that phi, should be equal to, phi should just be equal to this thing. And we now know that this constant is 0. So it's just going to be x cubed y. That's just going to be x cubed y plus, what was it? Half x squared y. Plus half x squared y and y squared. And we know that the constant is just 0. Okay, so that's basically what we know phi is equal to. Right, so basically the idea is if they're not exact, we come up with some integrating factor. If they're not exact, they're not, we come up with some integrating factor. So in other words, m with respect to y is not equal to m with respect to x. N with respect to x. Okay, then therefore we come up with some integrating factor. Which when we multiply by our functions and differentiate with respect to the corresponding, derivative, then it basically makes them exact. Okay, and that integrating factor is got out by solving this differential equation. So d mu by dx equals differential with respect to x. That becomes nx minus my. That's an n. That's over n. Okay, so that's mu. Okay, or we can solve the other way round. So d mu by dy. Look at y, so it's going to become my minus nx. Look at that m. It's going to be over m. Okay, times mu. Okay, so just solving either one of these differential equations, we'll find out what mu is, then just go about solving it in exactly the same way as we did before. So in other words, we say some function exists phi, such that when we differentiate with respect to x, it should be equal to not just m now, but mu times m. And when we differentiate that function with respect to y, it should be equal to not just n now, it should be mu times n. Okay, and then basically we kind of integrate it to find out what phi is. Okay, so we integrate one of these functions to find out what phi is, and then basically we'll have some constant on the end, and then we basically stick it. So then we basically stick it back. So we can equate it to, or we know that the derivative of the other function with respect to one variable is going to be equal to something. So therefore, if we differentiate it with respect to the same variable, then we can work out what c is. So basically, the idea is then we just work out what c is, and then that's just basically the method behind it.